This is problem 7-84. It is on page 364. Draw the shear and moment diagrams for the beam. Well, that's an original statement, isn't it? All right, let's see what the beam looks like so that we can figure out what the shear and moment diagram would look like. There's a simple support at A and B. Of course, part of the beam is cantilevered off or just continues past the support. There's a distributed load between A and B, magnitude 40 kilonewtons per meter. That occurs over an 8-meter span between A and B. There are 3 meters more sticking out at the end with a 20 kilonewton point load, and finally a 150 kilonewton meter moment applied at the end point. So the first thing to do is to sum moments about point A, taking counterclockwise as positive, so we can calculate the reaction at B. So we've got what? Negative 40 kilonewtons per meter times 8 meters worth, that's the resultant. And then the moment of that resultant would occur in the center of the 8-meter span, so a 4-meter moment arm. And of course it's a negative moment about A. B would provide a positive moment, but it acts 8 meters away from A. And then let's see, the 20 kilonewton point load would cause also a negative moment about A. Its moment arm is the entire length of the beam, 8 and 3, which are 11 meters. And then the 150 kilonewton load is a moment that is in the negative direction, and as usual, that point moment does not depend on where it's applied in terms of its effect on the moment equation itself. So all we're left with is an equation where B is the only unknown. Now I won't go through the algebra, but B came out to 206.25 kilonewtons when I ran through the equation before and calculated B. That's the solution to that equation. When we sum forces in the y direction, that will allow us to find the reaction at A. I'll write them so far as A and B because those two are the only ones acting upward. And then the 40 kilonewton per meter for 8 meters distributed load will give us the magnitude of the resultant of that distributed load. And then finally we have minus 20 kilonewtons. And those are all the forces that act in the vertical direction. So from this, you can solve for A, since of course you know the value of B, or the magnitude of B. And that's 133.75 kilonewtons. Fine. So we've got the reactions at the supports of the beam, but again, that's not the point of these problems. So the point is to get the shear and moment diagram. So let me make a shear and moment diagram immediately below the beam. So shear in kilonewtons and moment in kilonewton meters. We put the horizontal axis about in the middle on the shear diagram, and roughly in the center, maybe a little bit lower in the moment diagram. We know that shear has to begin where? Well, if we take a free body of just a little segment of the beginning of the beam, the shear would have to be equal to the reaction A, because we haven't had time for any significant distributed load to accumulate. And so the shear is simply equal to A at, let's see, I actually ticked off a decent scale here, but oh well, I'll just make a rough estimate here. So 133.75 kilonewtons should be the value of shear initially. Now, of course, that shear decreases at a rate of 40 kilonewtons per meter. So over 8 meters, let's see, 4/8 are what? 1632. So 320. So we should have a change of 320 kilonewtons as we go from our initial point of 133.75 down to a final point. And so if you take 133.75, subtract off the 320, you come down to a value of negative 186.25 kilonewtons. And of course, the shape of the graph between those 2 points is a straight line. So there's a linear decrease. And if we were to try and write out the equation of that line, it's easy. It's the intercept, 133.75, minus 40, the slope due to the distributed load, times x. So if you plug in x equal to 8, you'll get this point, negative 186.25. Now, let me move that 8 over just a bit. It just indicates the position on the horizontal axis along the length of the beam. At this point, we've got a point load that is a reaction of 206.25. So if we take 206.25 from we'll take 186.25 from 206.25, we'll find the magnitude of the shear at this point. And that comes out, despite my drawing, that comes out to 20 kilonewtons. And of course, once we reach the end, the last load brings the shear back down to 0. So basically, the shear as a function of position, well, it's not really a function of position, it's just constant, from 8 meters out to 11 meters along the length of the beam. And so the next thing to do is to begin our moment equation or our moment graph at 0, because there's no moment at the end, and integrate along the length of the beam, the shear equation. So if we were to calculate the change in moment by integrating the shear equation over the length of the beam, let's start off. Of course, this equation is only valid from 0 to 8. So 0 to some position x where x is less than or equal to 8. And so what would that look like? Well, v of x is 133.75 minus 40x and then dx. So integrating this is pretty straightforward. It's 133.75x minus 40x squared over 2. So there's not much more to say. We could simplify this and make it 20. But then it needs to be evaluated from 0 to x. But what we'll get back is exactly what we have, because when you plug in x equals 0 at the lower limit, that will drop off. You'll just get a big 0. So there's the equation of the moment from 0 to 8. Now, if we were to draw this, it is a parabola. If we plug in, for example, x equals 0, we get 0. If we plug in x equal to 8, so if you evaluate this at 8, notice the change, I'm confusing you probably, the moment as a function of x is the initial moment plus the change in the moment, but of course this initial moment is 0. So if we want to calculate the moment at x equal to 8, all we'd have to do is plug in x equal to 8, and that would give us the value of the moment. So if you do that, what you'll find is that the moment comes out to negative, I'll just put it over here, negative 210. If I can write it a little bigger. And the right number. There we go. So negative 210 kilonewton meters. But somewhere, notice we were adding up positive areas. So somewhere, in fact, where v is equal to 0, we must have had a maximum value of the shear. And in fact, we did. How could we evaluate it? Well, if we find where the 0 crossing of the shear occurred, then we could determine what that position is and plug it into our equation, or evaluate it, I guess, at x equal to that position, and come up with the magnitude of the moment at that point. So where does the shear cross 0? Well, how can we figure that out? Well, let's see. We've got to eliminate 133.75 kilonewtons. We eliminate 40 kilonewtons per meter, so after 1 meter, we've eliminated 40 of those 133.75. In fact, at 3 meters, we're almost done, because 3 times 40 would be, what, 120. But the easy way to do this is to say, well, let's take 40 kilonewtons, better yet, 133.75 kilonewtons per 40 kilonewtons per meter, and look what happens. We get meters out of this. Now, if you do the math, you'll find this is 3.34375, and I don't think I rounded that off, as I recall. So 3.34375 is the x value where we expect to find the maximum moment. So now we can use that x value in our equation which is evaluate the moment at x equal to 3.34375, and it would be 133.75 times 3.34375, run out of space, so minus 20 times 3.34375, quantity squared. Now that value of moment, if you plug all this into your calculator, tells you where the moment diagram should be at that particular position. When I did it, I found that this is 223.613. And of course, we've got a parabola where we're adding area very quickly at the beginning, so we expect something like this. It gets to a maximum here, so we've got a tangent line at the top that is horizontal, and then continues down something like that. So notice we're losing moment over here, but we're still positive, right? We're just losing it quicker and quicker because we're adding more and more negative area at a larger rate. Well, then what happens? Well, we'd like to integrate the shear from x equal 8 all the way to x equal 11. Take the same approach. But the shear equation is very simple. It's just 20. And so the integral of that 20 with respect to x is just 20x. We need to evaluate this from 8 to x. And so what does that look like? Well, it's 20x minus 20 times 8. Okay? Or in other words, this is 20 times x minus 8, if you like. Okay? So there's the change in the moment from this point all the way to x equal 11 from x equal 8. So if we want to calculate or write down, say, a functional form, m of x for, oh, and I guess I forgot to jot down the functional form over here, but if we want to write down the functional form from x equal 8 to x equal 11, then it would have to be, well, let's see, the initial moment, negative 210. It's not 0 anymore. There's our initial moment. Plus the change in moment, so 20 times x minus 8. And what that'll do for us is give us the moment as a function of position. Notice this is just a straight line. We could simplify it a bit if we wanted to. Negative 210 plus 20x, and what, 2 8s are 16, so minus 160, right? And so, hopefully I do all the math right, I'm doing it in my head. Yeah, 2 8s are 16, so that makes sense. So then if we add this together, that's negative 370 plus 20x. So there's the equation of the line. Here, notice it has a slope that is positive, right? And it has a y-intercept at negative 370. Now, we really don't care about that. If we plug in x equal to 8, then we get 160 here, and we'd be at negative 210. That's what we expect. If we plug in x equal to 11, so the moment evaluated at x equal to 11, we get negative 370 plus 20 times 11. Okay. 20 times 11 is what, 220? So 220 added to negative 370 comes up to what, negative 150? So this comes up to a value of negative 150, and sure enough, there's a moment at the end that completes it. Okay, so the equation of the line in this segment is m of x equal to negative 370 plus 20x, and unfortunately I erased the equation for the moment diagram earlier, but I can write it down. Let's see, that was the change in the moment. Moment starts at 0, so in fact the equation would be 133.75x minus 20x squared. So that gives us the shear and moment diagram along with all of the relevant points within the beam. For example, we know there's a maximum moment of 223 in the beam. And usually what causes failure in beams is not the shear load, but the moment load. And so it's always beneficial to know where the maximum moment occurs and its value, because that's where the beam is most likely to break initially.